The idea of power is that we are looking at the amount of energy used in a certain given time period. So we go back to that example we started the chapter off with. The weightlifter is lifting a barbell over his or her head. Now, if you have the same amount of weight and one person lifts it up like this, or the other person lifts it up really quickly, we talked about that's the same amount of energy still, which is kind of misleading. It's the power that's different. Power, again, is the amount of energy you exert in a given time period. Power is the amount of energy you exert in a given time period. So the amount of energy I exert by lifting the barbell over my head is the same as the amount of energy that Reese does. But if Reese can lift it up faster, he is more powerful, or he's generating more power. So power is the rate at which work is going to be done. Okay, the rate at which work is going to be done. Let's take a look at our definition and our equation for power here. We've got either one of these two formulas you can use. They mean the same thing now. So power is the amount of energy that's been changed over a given time period, or you could say the work done over a given time period. Because the work is the same thing as the amount of energy that's been changed. So depending on the problem, we'll use one or the other formula here. On your formula sheet, and you're welcome to look at it, you're going to be given one of those formulas. It's the first one here. So you're going to be given this on your formula sheet. You need to remember that delta E is the change in energy, which is really also considered the work done. Okay, the work done. Now, there's a third formula for power. So these are the first two. There's a third formula also. The third formula comes about if we plug in FD cosine theta for the work. Remember, work done is FD cosine theta. FD cosine theta. That's from section 5.1. If I am pulling on an object, okay, if I'm pulling on an object, I'm doing work on the object over a certain distance. That's where this is coming into play. Now, for this topic of power, we're going to be looking when theta is going to be 0. Okay, to simplify things a little bit. When theta is 0, what's the cosine of 0? -1. Positive 1. Cosine of 180 is -1. Whose iPad is on their keyboard? It might be, so just move it off. You can't be on the keyboard, else it'll make that noise. But I think it was that, yeah.
Yeah, it was that.
So cosine of theta is just 1 in this case, so we don't have to worry about it. So this equation becomes the following. Now, I'll scroll up so you can see it. What is this expression? I'm going to circle it in black. What is this equivalent to? What's d over t? What is it? Yeah, speed. Let's go with speed. Velocity would be x over t. So the distance you move over a given time period is your speed. So this formula really becomes power equals force applied times speed. Okay, so this is another formula that's going to be given on your formula sheet. So you're going to be given that formula, and you're going to be given this formula. Okay, those two. Now, remember that the one with the delta E could also be written like this. Could also write it this way, work over time. Okay, work over time. But you're given the two ones that are boxed in there on the test or on your formula sheet. Mike?
Is this like the kinematics thing where you have to decide which one you're going to use based on like what the problem is?
Yeah, all of our problems are like that, not just kinematics, all of them. Same thing with forces. You have to figure out which force formula you're going to use. So it's the same as it's been all year. You're given several formulas, okay? You have to figure out based on the parameters of the problem what you're going to actually use. So these are the main two. Okay, these are the main two right here, but change in energy is also known as work. So you could use this formula instead of this one as well. But you're given these two. Just a quick update. I changed one thing on your formula sheet, so if you want to re-update your formula sheet, you can in Notability. It won't make much of a difference. If you remember, on the formula sheet in the past, I had like fx equals f cosine theta and fy equals f sine theta. I don't know why it was on the formula sheet. I didn't mean for it to be there, so I took it off. So on your test, that's not going to be there, but it really doesn't affect this chapter. But just to give you a little heads up. I also changed, last year when I taught work, instead of using this formula for work, FD cosine theta, I used F, absolute value of x, cosine theta. It's the same thing, and that's on the old formula sheet, but it confused students last year, so that's why I'm using FD cosine theta this year. So if you loaded the last formula sheet in the beginning of the year, you might have for work, you might have work equals F cosine theta, absolute value of x, which may be a little bit confusing. So if you want to reload the new formula sheet for work, you'll have this formula right here on the top. FD cosine theta for work. Okay, so if it confused anybody, I apologize. What are the units going to be for power? And I put it already up top so you can scroll up and take a look. What is the unit? Watts. What is watt defined as? What is it used? It's used in light bulbs.
Joules over second.
What is it, Mike?
Joules over second.
Yeah, joules per second. So watts, remember, watts are the rate of change of energy. How do I know it's a rate of change? Because it's over time. It's over time. So a watt is really a joule per second. But yes, you've heard of watts with energy bills like kilowatt hours or light bulbs like a 60-watt light bulb. Okay. Now we're going to talk about electrical power later in the year where we look at light bulbs and different things like that. We'll do circuitry and you'll see light bulbs light up. But for this example, when we talk about watts, we're talking about mechanical power. Mechanical power as opposed to electrical power, which we will look at later in the year. So the wattage, okay, here we're looking at mechanical power. Mechanical power. All right, so again, we have really three formulas that we can choose from. The two in the boxes are given on your formula sheet. You should know that change in energy could also be work. So these are the same thing, really. Depending on the problem, we'll pick one of these three. Is that clear so far? All right, let's go on to the first example. In the first example, we have two horses pulling on a cart. So like a wagon maybe, like Oregon Trail style. Each exerts a force of 250 newtons. So each horse is pulling with 250 at a speed of 2 meters per second for a time period of 10 minutes. Part A, we want to calculate the power delivered by the horses. So mechanical power. By the way, this is where horsepower comes from. You know that?
Oh.
Horsepower is a rating at which horses would pull a certain amount of coal out of a mine shaft in a given time period. That's what horsepower came from. So back in the day, when they didn't have ratings of like wattage, they used horsepower before we started looking at the electrical stuff. And the amount of power that the horses produced pulling a certain mass of coal out of a mine shaft in a given time period was considered horsepower. That's where it actually comes from. So anyway, to go back to horses, that's why I use this example here. So for part A, we're going to calculate the amount of power delivered by the horses, and part B, how much work the horses do. So let's list our givens to start this problem. Let's list our givens. What's one of the given pieces of information here? Maria?
Force equals 250 newtons.
Per horse, right? So how much newtons altogether? Again, there's two horses. They're each pulling with 500 newtons. So how much pull is really happening here? Because we're looking all together. The power delivered by the horses, not the horse, singular. Horses. Okay, 500 newtons of force. What is the speed? 2
meters per second.
And then finally, what about the time?
10 minutes. Wait, but Mr. Howe?
Mike?
Wait. No, never mind, I just answered it.
Okay. Are we good? What do we have to do? There's one thing we have to do. Very good. Okay, 600 seconds. 60 seconds in a minute, so after 10 minutes you have 600 seconds. If you need to use dimensional analysis to convert there, you can multiply 10 minutes by 60 seconds per 1 minute. Cancel the minutes, you end up with 10 times 60 or 600 seconds. But use logic also, right? After 2 minutes, it's 120 seconds. After 3 minutes, it's 180 seconds. It's 60 seconds every minute, so 60 times 10 is 600 seconds. Now, we've got three pieces of info here: force, speed, and time. And I've got three formulas. List the three formulas for me. What's the first formula we could choose? I want all three and then we'll pick.
E equals W over T.
Work over time, that's the first one, okay? What's another one? Mike?
P equals delta E over delta T.
So change in energy over time. And then the last one was what?
Bless you.
P equals F times speed.
Which do you think we're going to use to find part A? Yeah, the last one. Look at what you've got. You've got the time, so it's tempting at first to use one of the first two. But you don't have the work done. You don't have the energy change. So you can't find that information out yet. but we do have force and we do have speed. So let's go ahead and use the third formula for part A.
What do you? Oh.
You sure? I'll slide it up so you can see. Okay, so we're calculating the power delivered by the horses. There are two horses. Together, the force they apply is 500 newtons. They apply this force at a speed of 2 meters per second. 500 newtons times 2 meters per second gives me 1,000. And my units of power are watts. Okay, my units of power are watts. How about part B? How much work is done by the two horses? How much work is done? Which of the three formulas might I use now, Maria?
P equals W over T and then solve for W.
Yeah, power equals work over time, because I'm trying to find the work done by the horses. So we can solve for W. How do we solve for W in this equation? How do I solve for W, Catherine?
Multiply both sides by 2.
Yeah, bring up the T. Power times time is work. So if we want to find the work done by these horses, we have the time period. The time period was 600 seconds. We've got the power generated from part A. We can plug in.
TP.
TP.
Do you have a TP house?
Okay. So 1,000 watts times 600 seconds is 600,000. All right, 600 times 1,000, 600,000. What are my units for work? For work.
Joules.
Joules, very good. Remember somebody asked a question earlier in the chapter? And the question was, joules are very small values, so we're going to get large answers. So should we use scientific notation or any prefixes? Here you could if you wanted to. You could write this and you could say, well, this is just 600 kilojoules. Okay, it's the same thing. No different. Okay? You don't have to do that, but you have to know how to convert. So on the test, if I tell you that the work done is 600 kilojoules, you should know that it means 600,000 joules. Because your prefix kilo means 1,000. So kilojoule means 600,000 joules. Again, this is how I translate. Okay, I'll show you. I'll move it up so you can see. I personally translate this as the following. 600,000 joules, which is what it really is. Okay? So you should be familiar with converting, absolutely. Always. For any test, you should be able to convert. That's why that was in chapter 1, or the first thing we learned.
Multiply from kilojoules to joules, you multiply by 1,000.
Correct. Same thing you did with kilometer, right? If you have 3 kilometers, that's 3,000 meters. All right, example. Now this example we can do 2 different ways, and I want to show you both methods. We'll begin by taking a look at our givens first, and then we'll go into the problem. Can I get someone to read this for us? Can I get someone to read this for us? Go ahead, Nick.
How much power is needed to lift an elevator with a mass of 500 kilograms if it travels at a constant rate or a vertical distance of 100 meters in 15 seconds?
So what are our givens in this problem? What are the givens in this problem? Elliot? Wow, sorry, Reese?
M, D, and C.
Yeah, so M is?
500, D is 100, and then T is 15.
Now, here's my question for you. This elevator is moving which way? Which way do elevators move? Vertically, right? Vertical distance. So, I could technically say the following. Ready? I could say that yi is 0, starts at the ground. And then what would yf be? Yeah, 100. So I could use this instead of d. Instead of looking at it in distance terms, I could say that the yi is 0 meters, I'm starting at the ground, and the elevator moves up to a height of 100, so yf is 100. So we're going to solve this 2 different ways here. We'll solve it using energy and we'll solve it using work, but they're the same thing. So we'll get the same answer. But I want to show you that it doesn't really matter. One way is easier than the other though. So we'll go through this and decide which way is easier. So if we want to find, again, how much power is needed, we're looking for power. We have nothing with force in this problem. We have nothing with speed in this problem except that it's a constant speed. So we're not going to use the formula that says P equals F speed, because again, we don't have a force, and we don't have the speed there. So that might not be very useful, right? So let's go and look at the other two formulas, and I'll split the page up. We'll start on this side with power equals work over time, and we'll do over here power equals change in energy over time. What's my formula for work? Now, here's the tougher part on the right-hand side. What's delta E going to be replaced by? Change in energy.
PE and JE.
Close, you had it in the beginning.
P just PE.
But what about PE, Mike?
P.
The object starts here, right?
Yeah.
It starts to move at a constant velocity, and then it stops at the top.
So PEI minus PEF minus PEI.
Yeah, so potential energy at the end minus potential energy at the beginning.
Why does that matter?
What do you mean?
Like, why is it PEF minus PEI?
Final minus initial. You'll get a negative answer, pretty
Oh,
much.
okay.
You'll get the opposite of the answer you want. Always final minus initial. Anytime you have delta in any situation, math, physics, chemistry, anything, delta means final minus initial. So in this problem, the elevator is moving 100 meters up, okay? So we know that there's a change in only potential energy. The reason there's not a change in kinetic energy is because it's moving at a constant speed. So ready, watch. I'm running at 5 meters per second, and I'm still running at 5 meters per second. My kinetic energy isn't changing. Sure, I have kinetic energy, but it's not changing. It's not changing. The formula for power is defined as the change in energy. The change in energy. So yes, there is kinetic energy in this problem because the elevator is indeed moving up. Right? It is moving up. So there is kinetic energy. But this problem is not about whether it's before and after for kinetic energy because the kinetic energy is consistent the whole way. So what is the type of energy that is changing? The type of energy that is changing is potential energy because it's starting at the ground and it's ending up at the top. If it starts at the ground, what can I do with my potential energy initial?
Zero.
Why can I make zero there? Who can tell me why would it be zero?
You're starting off with the ground, which is 0, and then anything times 0 is 0.
Yeah, anything times 0 is 0. And if you remember your formulas,
It has no height.
it has no height. So here's our formulas. Ready? This would become the following. mgyi minus yf. See, I just did that, Mike. Sorry. mgyf minus mgyi all over t. But this has no height in the beginning, so it doesn't matter. Okay, on the right-hand side here, there's no height for yi, so it does not have any significance on the problem. Now, on the left-hand side, though, the elevator is moving vertically. The force applied. If you think about an elevator, what's moving the elevator up and down? The cables. Which way do the cables pull? Up and down, right? So if I'm moving up and the cable's pulling up, there's no angle between those two vectors. The object is moving up, the actual pull is upward, so what would theta be?
100. No.
90.
0.
I heard 180, I heard 90, I heard 0.
90. Wait, can you repeat the question?
Alright, let's repeat the question, ready? So in the past we said, in the past, not for this problem, if the force is this way and friction was this way, it was 180, right? We talked about that?
Yeah.
Okay. If the force is this way and the motion is this way, the two lines lie on top of each other.
So it's zero.
So it's 0. There's no angle between them. Same thing goes for vertically. The vertical motion is up. The force is upward. So both of these lines lie on top of each other. It's not like I'm pulling this way and I'm moving this way. Then there would be a little angle between them, right? But there's no angle between them because the force is up and the motion is up. So the cosine theta doesn't affect this, just like we said a moment ago. So this doesn't have any play or any effect on the problem. Now the question becomes this. What is the force in this problem? What is the force? We know the distance. We know the time. So we've got that on the left-hand side. Okay, we've already got all the info over here. We can come up with our answer on this side. So I'm going back over here now. What is the force that the cable is pulling up with?
Well, don't have normal force because of the weight. So
Okay.
wouldn't the normal force be 500 kg?
Close. That's a mass.
So the F times Fn equals Fg.
Yeah, very good. So, in this problem, when you have an object moving at constant velocity, we're in a state of equilibrium. When we're in a state of equilibrium, we have a balance of forces. That means the following. The weight of the elevator pushing down needs to be compensated by the actual cable pulling up. So Mike was talking about normal force, which is in essence what this is. So the cable is providing a force upward that's equal to the weight pulling downward. So this force here is the cable pulling up, but it's equal to the weight. And the weight, if we remember, is Fg. So this is really, in essence, Fg. Okay, and Fg is equal to mg. So take a look at your answer now.
No, I'm confused.
Okay, hold on. Take a look at your answer here. Fg is the weight that is replaced with mg. This is the same thing. They're absolutely identical. mg, yf, mg, d. yf and d are both 100. So it's no change in the problem. These are identical to one another. So either way you can solve. Personally, I would choose the potential energy. Can we stop? Just move the keyboards aside. Come on, that's like the 8th time that's happened. Please, guys. The change in energy is a lot easier to do than it is to do the work part here. Okay, the work part is a little confusing because then you have the angle involved and stuff. But if you can see that the change in energy is only potential, then please just use this formula. This one is far more confusing to go through. So I want to show you that it turns out to be the exact same thing. It's no different, but one way is definitely easier than the other. Camila, you said you were confused. What's your question?
With the FG, like, how did you move?
Okay, so when an object is in a state of equilibrium, we know that the pull up needs to be equal to the push down. So right now, if I looked at this mouse on the table, the weight acting down is equal to the normal force pushing up, and we've done that many times. But now there's no normal force, because we're not looking at that. We're looking at a cable pulling up the elevator. If this object is moving at a constant velocity, it means that the sum of the forces is 0, we're in equilibrium, so the weight acting down is equal to the cable pulling up. So this F is really the cable pulling up, but we don't know what that force is. But we do know the weight of the object, and the weight of the object is Fg. So we can replace this with just mg. Whatever the weight of the object is the force of the cable pulling up, because we're moving in equilibrium. And this goes back to the last chapter. That's why that last chapter with forces was so important. You're going to see it occurring over and over again. You're going to hear about forces.
So they're only the same equation if there's no initial, right?
No initial what?
No initial potential, so no initial energy.
No, they'd still be the same.
Also, if there's like,
Watch, if I started at 10 meters
yep,
and I went up to 100 meters, what's my change? How many? 90 meters. If I start at 10 and I go to 100, that's a change of 90 meters, right? So that would mean that my distance would just be 90 meters instead, and this would be YF would be 100 and YI would be 10. You would get the same answer. Okay? We get the exact same answer. So the idea is that distance in this problem traveled is equal to the change in height, really. That's what the YF is. So again, let's go back and just reiterate what we did. How much power is needed to lift an elevator? The mass is 500. So we use the mass. We're going to use that to find the weight in this part. Or we're going to use the mass and the potential energy to find the actual change in height. It's moving at a constant rate, which gives us equilibrium. The vertical distance is 100 meters in 15 seconds. So either we could say that the distance is 100 meters, or we could say that yi is 0 and yf is 100. Same exact thing. Two different solutions. Plug in your numbers now and see what you get, please. Do it both ways. Don't just do it one of the ways. Plug in your numbers and see what you get for both of them. I'll give you a minute to do it. It should be pretty obvious that the answers are the same just by looking at when you plug in.
We use negative 9.81.
Positive. Again, negative 9.81 was only used with acceleration in kinematics. Catherine, what do you got for a number?
32,700.
Very good. And good, units of watts. What would that be in kilowatts? In kilowatts, what would that be? Good, 32.7. 32.7 kilowatts. Okay? So again, these problems, you're going to notice that you can choose one way or the other. It's up to you to choose the easier way. So when you see something that's only changing vertical height, I would recommend using some sort of energy method instead of work done. If you're given a force and a distance and that kind of stuff, then you probably want to use the work done because it's easier. Mike?
If it's like the final equation is P equals mgYIF over T, why is like the yi up there like why isn't it 0? 'Cause
It is 0. That's the 0 right here.
then what's the 100 meters? Why?
This is the YF, the final height of the elevator. It starts at 0 and it ends at 100 meters.
Oh, so it's both the initial and the final YIF.
Again, this is just YF here. There's no I there. That was just my typo. I said that before.
All right.
This here, Mike, you're talking about, that's YF.
I thought it was YI.
Sorry, this is YI right here.
Okay.
This becomes 0. This YF is the 100 right there.
Yeah. Then,
Okay.
Then,
Philip?
So if on a test you wrote a question and it said 32.7 kilowatts, we multiply that by 1,000?
Correct.
Alright.
Correct. Bobby? Yep. Camila?
Are distance and YF always the same in these problems?
No, because what Smitty asked before, if the distance is 100 and I started at like 20 meters, this would become a 20 and this would be 120. But the change in them is still 100. Again, if I call ground level to be 20 meters and then I would go up to 120 meters, the change is 100, but the YF would then be different from the D. Okay? But you would get the same answer for power. You get the same exact answer for power. So either way is fine. The last example here. If a car with a mass of 1,800 kilograms accelerates from a velocity in a straight line of 3 meters per second to 10 meters per second in a time period of 15 seconds, then what is the average power delivered by the car's engine? Let's list our givens. What do we have for givens here? This is a misleading problem, that's why I want to go through it. What's our givens in this information? Smitty?
The initial and final velocity.
Good. It's in a straight line, so we don't have to worry about differentiating between velocity and speed. They'll be the same thing. Initial is?
Initial is 3 meters per second. And then 10 meters per second.
Okay. What else do I know? What else do I know here?
time.
Reese?
Charge was 15, and then mass, which is h/100.
All right. So we've got all of our information given. It is extremely tempting to use a formula that involves speed because you see there's a velocity here. So at first you might say, let's use the power equals force times velocity or force times speed formula. But the problem right now is that we don't have a force. We don't have a force. So it's a little bit more work to get a force. So I'm not going to go that route. We could if we wanted to. But we're not going to go that way. There's an easier way to do this. If the object is moving along the ground only, what can we say about the potential energy? Scott? Yeah, there's no change in potential energy. Right? If I'm traveling in a car and I'm riding along a horizontal surface, I'm not changing any height. So my potential energy doesn't change. What energy is changing in this problem, Mike?
Kinetic.
Kinetic. So let's go to our formula that says the following.
So isn't it this pretty much the same as before? It's P delta E over delta T, but instead of potential, it's kinetic.
Very good, Mike. Well done. Okay, so this is what we're going to do instead. In the last problem, we did the potential final minus potential initial because it moved vertically. But now the object is changing speed. Because it's changing speed, we're going to use a change in kinetic energy. This becomes 1/2 mvf squared minus 1/2 mvi squared all over time. Okay, all we're doing at this point is plugging in our formula for kinetic energy. Okay, plug in your formula for kinetic energy for each time. Now, if you'd like to, you're welcome to to factor out the 1/2 m. You don't have to. You can though. Okay, and that's what this would look like if you did. Okay, so you could factor out the 1/2 m. Why can I do that? Because it's in both terms. Good. It's not in the bottom though, so we can't cancel it. Remember that? You can only cancel if it's in every single term. It's not in the bottom there, so we cannot cancel the 1/2 m. But we see that it's in both of these two, so we could factor it out in front. And if you redistributed, you would get back to this line to prove that you're true. Okay? You know all that information. You can go ahead and plug in. Okay, you can go ahead and plug in now. You know the mass, you know the final initial velocity, you know the time period. Plug in and see what you get for the power. It's 1800 for the mass?
Yeah.
Make sure you square your numbers before you subtract them. Please, 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 don't subtract 10 minus 3 and then square it. You need to do 10 squared minus 3 squared. Order of operations. Exponents come before subtraction. Very different numbers, you'll notice, if you did it the other way. What do I have for a number? Anybody have a number for me? Joyce?
5,416
5460
Yeah.
units of?
kilowatts.
What is it?
Watts.
It's in watts. You could convert it to kilowatts if you'd like to. 5.46 kilowatts is fine, but it's in watts, the answer you get. Okay, there's your answer up there in watts. I want to make one statement about this, because there is something you should know. What was the theorem in section 5.2? What was the theorem that we learned in 5.2? Anybody remember what it was called?
Something work theorem.
Yeah, work kinetic energy. Good. Work kinetic energy theorem. And in that theorem, we were told that the amount of work done by an object whose speed changes is equal to the change in kinetic energy. That was work equals delta KE. Technically, this problem, we're using that. Because look, remember this is our formula up here? Power equals delta E over delta T. Well, didn't we also write this with a W earlier up here? Didn't we say that earlier we could just call this W over T instead? That's another way of writing this. And in the end, we're replacing this W with KEF minus KEI. So in essence, we could have used work over time and said, well, work is defined as the change in kinetic energy by using the work kinetic energy theorem. So we could have said this and then gone right to this and continued the problem the same way. And it's the same answer. Okay, so the idea, again, is that our change in energy here is only kinetic. So we could use the work kinetic energy theorem and use it as well. It's no different. Either way you want to look at this problem is fine. If you have a change in speed, you have a change in kinetic energy. That's all that matters. So you could use the work kinetic energy theorem, or you could just say delta E and then use KEF minus KEI. Okay, but it's the exact same answer. You would still use the exact same variables. Nothing would change. The problem would be identical for the rest of it. Okay? I'm going to stop here. Your homework, what is it? There's 2 problems at the top and 1 at the bottom. Now, here's what I want to do. Since your problem set is due tomorrow, bless you. Since your problem set is due tomorrow, and it's on 5.1, 5.2, 5.3, and 5.4, do that tonight. Wait for this. I'll make this due on Monday. Okay, well, actually, technically it's going to be due on Tuesday. I'm not going to be here on Monday. Okay? So it'll be on Tuesday. But I don't want you to focus on this tonight. I'd rather you work on your problem set because, in essence, you're going to do 5.4 anyway in the problem set. Because there's 1 or 2 questions from 5.4 in the problem set anyhow. If you finish the problem set and you want to be proactive and get this done, it will help you for sure. But try and do this before your test anyhow. Okay, try and do this before your test. Your problem sets are due tomorrow. Please have them done so I can put the solution up over the weekend. Okay, please have them done. Even if you don't turn it in tomorrow, please turn it in as soon as possible over the weekend so that I can then put the answer key up. I'm not going to email people this time. I'm tired of it. Okay, last time I emailed 5 people that didn't turn it in, and ended up 2 people just didn't get back to me. So if you don't hand it in tomorrow, and there's like 2 people missing, the whole class is going to suffer. I'm not going to hound you over the weekend and email you over and over again to turn it in. So if that happens, it's unfortunate.
For the problem sets for 5/4.
I updated it. Yeah, take a look. I updated it. Take a look again. So if you go to Moodle, for section 5.4 on the problem sets, it said like page 193 and there was no question listed. Okay? I updated it. I just got rid of that. So just ignore that. Okay? Let me think, what else? Your lab that you worked on. Please spend some time working on it this weekend because it will help you on the test. I'm not going to make it due on Monday because it's going to be a lot of stuff to do and I'd rather you study also. But it will help you study. I'm telling you now that the questions from your lab are very useful for your test. They are very, especially the multiple choice questions on your test. The lab will help you a lot with the multiple choice questions. I'm giving you a huge hint by saying that. So I would recommend you working on it this weekend, but I won't make it due. Okay, I won't make it due until Tuesday. So tomorrow your problem set is due. On Tuesday, homework 5.4 and the lab are going to be due. So you should get a jump start on some of those anyway, because the homework 5.4 and the problem set, they will help you. So I'd recommend doing them over the weekend, but on Monday for your test, I'm not going to be in school. I'm going to be away on this weekend, this whole weekend actually, leaving tomorrow afternoon. So after school I have to leave and I'm not going to be back until Monday night. So on Monday when you come in, you're going to get a test, you're going to get a formula sheet. Your proctor will know to give you both of those. If you have extended time, your test will already be torn off. You'll have the first 4 out of 6 pages there. If you finish early, I'm sorry, this time I can't give you another page to get started on. Okay, so when you come in for your extended time, you'll do the rest. I'm not going to make the proctor have to worry about all that. You clear what I'm saying? So on Monday, when you come in, make sure that you're ready to go right away. Camila, thank you.
What day is Monday?
Okay, Monday is the day 1. It happens to be an A day, so you have the full period, and it's day 1. Okay, the test, at the end, you're going to have a choice of problems again, just like last time with the last 2 to choose from. You have some short answer, you have some multiple choice, same format as always. Okay, no difference in format. If you have extended time, you need to email me by the end of, before class tomorrow at some point. Before I see you, because I'm going to see this class and tomorrow, and the other class tomorrow. Please tell me before you leave class at some point or email me about extended time. Because I need to prepare your test accordingly for the proctor if you have extended time. If you don't want to use your extended time, or if you don't email me, if you don't get ahead on that, then I'm not going to give you extended time. Just like always, you don't get extended time. Okay, so if I don't hear from you by tomorrow about extended time, I need to get this stuff ahead of time done for the proctor. So I can't do it over the weekend. I need to do it before I leave school tomorrow. I'm not here over the weekend.
No, I was just gonna ask you about the. Can I do what I did last time, like with the other class, like?
No, because it's a proctor. It's
Oh,
different.
okay. All right.
So again, Monday you're not taking the extended time. You have to take it on Tuesday. So look on. I'm not here on Monday, Mike.
Oh, all right.
For those with extended time, look on Tuesday, empty periods.
So day 2, right?
Yeah, so look on Tuesday, day 2, for when you're going to take the extra time. So it's not going to be on Monday. Your extended time will not occur on Monday. Okay?